हेलो एवरीवन। आज हम केमिस्ट्री क्लास 12 एनसीईआरटी की बुक से यूनिट 13 अमीन्स का रीडिंग करेंगे। ये एक ऑडियो बुक है रिवीजन पर्पस के लिए। अगर आपको बुक्स बाय करनी है तो डिस्क्रिप्शन में लिंक है, आप उसे चेक कर सकते हैं। द चीफ कमर्शियल यूज ऑफ अमीन्स इज एज इंटरमीडिएट्स इन द सिंथेसिस ऑफ मेडिसिन्स एंड फाइबर्स. Amines constituent an important class of organic compounds derived by replacing one or more hydrogen atoms of ammonia molecule by alkyl/aryl groups. In nature, they occur among proteins, vitamins, alkaloids, and hormones. Synthetic examples include polymers, dyestuffs, and drugs. Two biologically active compounds, namely adrenaline and ephedrine, both containing secondary amino group, are used to increase blood pressure. Novocaine, a synthetic amino compound, is used as an anesthetic in dentistry. Benadryl, a well-known antihistaminic drug, also contains tertiary amino group. Quaternary ammonium salts are used as surfactants. Diazonium salts are intermediates in the preparation of a variety of aromatic compounds including dyes. In this unit, you will learn about amines and diazonium salts. First, amines. Amines can be considered as derivatives of ammonia obtained by replacement of one, two, or all three hydrogen atoms by alkyl and/or aryl groups. For example, CH3NH2, C6H5NH2, CH3NHCH3, CH3 and CH3CH3. 13.1 Structure of amines. Like ammonia, nitrogen atom of amines is trivalent and carries an unshared pair of electrons. Nitrogen orbitals in amines are therefore sp3 hybridized and the geometry of amines is pyramidal. Each of the three sp3 hybridized orbitals of nitrogen overlap with orbitals of hydrogen or carbon depending upon the composition of the amines. The fourth orbital of nitrogen in all amines contains an unshared pair of electrons. Due to the presence of unshared pair of electrons, the angle CNE, where E is carbon or hydrogen, is less than 109.5 degree. For instance, it is 108 degree in case of trimethylamine as shown in figure 13.1. Figure 13.1 pyramidal shape of trimethylamine. 13.2 Classification. Amines are classified as primary, secondary, and tertiary depending upon the number of hydrogen atoms replaced by alkyl or aryl groups in ammonia molecule. If one hydrogen atom of ammonia is replaced by R or AR, we get RNH2 or ARNH2, a primary amine. If two hydrogen atoms of ammonia or one hydrogen atom of RNH2 are replaced by another alkyl or aryl group, what would you get? You get RNHR secondary amine. The second alkyl/aryl group may be same or different. Replacement of another hydrogen atom by alkyl/aryl group leads to the formation of tertiary amine. Amines are said to be simple when all the alkyl or aryl groups are the same and mixed when they are different. This is primary, this one is secondary, and this is tertiary. 13.3 Nomenclature. In common system, an aliphatic amine is named by prefixing alkyl group to amine, that is, alkylamine as one word, in bracket, for example, methylamine. In secondary and tertiary amines, when two or more groups are the same, the prefix di or tri is appended before the name of alkyl group. In IUPAC system, primary amines are named as alkanamines. The name is derived by replacement of E of alkane by the word amine. For example, CH3NH2 is named as methanamine. In case more than one amino group is present at different positions in the parent chain, their positions are specified by giving numbers to the carbon atoms bearing NH2 groups, and suitable prefix such as di, tri, etc. is attached to the amine. The letter E of the suffix of the hydrocarbon part is retained. For example, H2N, CH2, CH2NH2 is named as ethane 1,2-diamine. To name secondary and tertiary amines, we use locant N to designate substituent attached to a nitrogen atom. For example, CH3NH CH2CH3 is named as N-methyl ethanamine, and CH3CH2 thrice N is named as N-diethyl ethanamine. More examples are given in table 13.1. In aryl amines, NH2 group is directly attached to the benzene ring. C6H5NH2 is the simplest example of aryl amine. In common system, it is known as aniline. It is also an accepted IUPAC name. While naming aryl amines according to IUPAC system, suffix E of arene is replaced by amine. Thus, in IUPAC system, C6H5NH2 is named as benzenamine. Common and IUPAC names of some alkyl amines and aryl amines are given in table 13.1. Table 13.1 Nomenclature of some alkyl amines and aryl amines. 13.4 Preparation of amines. Amines are prepared by the following methods. First, reduction of nitro compounds. Nitro compounds are reduced to amines by passing hydrogen gas in the presence of finely divided nickel, palladium or platinum, and also by reduction with metals in acidic medium. Nitroalkanes can also be similarly reduced to the corresponding alkylamines. Reduction with iron scrap and hydrochloric acid is preferred because FeCl2 foam gets hydrolyzed to release hydrochloric acid during the reaction. Thus, only a small amount of hydrochloric acid is required to initiate the reaction. Second, ammonolysis of alkyl halides. You have read in bracket unit 10 class 12 that the carbon halogen bond in alkyl or benzyl halides can be easily cleaved by a nucleophile. Hence, an alkyl or benzyl halide on reaction with an ethanolic solution of ammonia undergoes nucleophilic substitution reaction in which the halogen atom is replaced by an amino in bracket NH2 group. This process of cleavage of CX bond by ammonia molecule is known as ammonolysis. The reaction is carried out in a sealed tube at 373 Kelvin. The primary amine thus obtained behaves as a nucleophile and can further react with alkyl halide to form secondary and tertiary amines and finally quaternary ammonium salt. The free amine can be obtained from the ammonium salt by treatment with a strong base. Ammonolysis has the disadvantage of yielding a mixture of primary, secondary and tertiary amines and also quaternary ammonium salt. However, primary amine is obtained as a major product by taking large excess of ammonia. The order of reactivity of halides with amines is Ri greater than Rbr greater than Rcl. Third, reduction of nitriles. Nitriles on reduction with lithium aluminium hydride in bracket LiAlH4 or catalytic hydrogenation produce primary amines. This reaction is used for ascent of amine series, that is for preparation of amines containing one carbon atom more than the starting amine. Fourth, reduction of amides. The amides on reduction with lithium aluminium hydride yield amines. Fifth, Gabriel thalamide synthesis. Gabriel synthesis is used for the preparation of primary amines. Thalamide on treatment with ethanolic potassium hydroxide forms potassium salt of thalamide, which on heating with alkyl halide followed by alkaline hydrolysis produces the corresponding primary amine. Aromatic primary amines cannot be prepared by this method because aryl halides do not undergo nucleophilic substitution with the anion formed by thalamide. Sixth, Hofmann bromamide degradation reaction. Hofmann developed a method for preparation of primary amines by treating an amide with bromine in an aqueous or ethanolic solution of sodium hydroxide. In this degradation reaction, migration of an alkyl or aryl group takes place from carbonyl carbon of the amide to the nitrogen atom. The amine so formed contains one carbon less than that present in the amide. 13.5 Physical properties. The lower aliphatic amines are gases with fishy odor. Primary amines with 3 or more carbon atoms are liquid and still higher ones are solid. Aniline and other aryl amines are usually colorless but get colored on storage due to atmospheric oxidation. Lower aliphatic amines are soluble in water because they can form hydrogen bonds with water molecules. However, solubility decreases with increase in molar mass of amines due to increase in size of the hydrophobic alkyl part. Higher amines are essentially insoluble in water. Considering the electronegativity of nitrogen of amine and oxygen of alcohol as 3.0 and 3.5 respectively, you can predict the pattern of solubility of amines and alcohols in water. Out of butane 1-ol and butane 1-amine, which will be more soluble in water and why? Amines are soluble in organic solvents like alcohol, ether, and benzene. You may remember that alcohols are more polar than amines and form stronger intermolecular hydrogen bonds than amines. Primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen of one and hydrogen of another molecule. This intermolecular association is more in primary amines than in secondary amine as there are two hydrogen atoms available for hydrogen bond formation in it. Tertiary amines do not have intermolecular association due to the absence of hydrogen atom available for hydrogen bond formation. Therefore, the order of boiling point of isomeric amines is as follows. Primary is greater than secondary is greater than tertiary. Intermolecular hydrogen bonding in primary amines is shown in figure 13.2. Figure 13.2 intermolecular hydrogen bonding in primary amines. Boiling points of amines, alcohols and alkanes of almost the same molar mass are shown in table 13.2. Table 13.2 comparison of boiling points of amines, alcohols and alkanes of similar molecular masses. 13.6 Chemical reactions. Difference in electronegativity between nitrogen and hydrogen atoms and the presence of unshared pair of electrons over the nitrogen atom makes amines reactive. The number of hydrogen atoms attached to nitrogen atom also decides the course of reaction of amines. That is why primary, secondary and tertiary amines differ in many reactions. Moreover, amines behave as nucleophiles due to the presence of unshared electron pair. Some of the reactions of amines are described below. First, basic character of amines. Amines being basic in nature react with acid to form salt. Amine salts on treatment with a base like NaOH regenerate the parent amine. RNH3 plus X minus plus OH minus will form RNH2 plus H2O plus X minus. Amine salts are soluble in water but insoluble in organic solvents like ether. This reaction is the basis for the separation of amines from the known basic organic compounds insoluble in water. The reaction of amines with mineral acids to form ammonium salts shows that these are basic in nature. Amines have an unshared pair of electrons on nitrogen atom due to which they behave as Lewis base. Basic character of amines can be better understood in terms of their Kb and pKb values as explained below. RNH2 plus H2O will form RNH3 plus OH minus. K is equals to RNH3 plus OH minus upon RNH2 into H2O, or KH2O is equals to RNH3 plus OH minus upon RNH2, or Kb is equals to RNH3 OH minus upon RNH2. pKb is equals to minus log Kb. Larger the value of Kb or smaller the value of pKb, stronger is the base. The pKb values of few amines are given in table 13.3. pKb value of ammonia is 4.75. Aliphatic amines are stronger bases than ammonia due to plus I effect of alkyl groups leading to high electron density on the nitrogen atom. Their pKb values lie in the range of 3 to 4.22. On the other hand, aromatic amines are weaker bases than ammonia due to the electron withdrawing nature of the aryl group. Table 13.3 pKb values of amines in aqueous phase. You may find some discrepancies while trying to interpret the Kb value of amines on the basis of plus I or minus I effect of the substituents present in amines. Besides inductive effect, there are other effects like solvation effect, steric hindrance, etc., which affect the basic strength of amines. Just ponder over. You may get the answer in the following paragraphs. Structure basicity relationship of amines. Basicity of amines is related to the structure. Basic character of an amine depend upon the ease of formation of the cation by accepting a proton from the acid. The more stable the cation is relative to the amine, more basic is the amine. A. Alkanamines versus ammonia. Let us consider the reaction of an alkanamine and ammonia with a proton to compare the basicity. Due to the electron releasing nature of alkyl group, it pushes electrons towards nitrogen and thus makes the unshot electron pair more available for sharing with the proton of the acid. Moreover, the substituted ammonium ion formed from the amine gets stabilized due to dispersal of the positive charge by the plus I effect of the alkyl group. Hence, alkyl amines are stronger base than ammonia. Thus, the basic nature of aliphatic amines should increase with increase in the number of alkyl groups. This trend is followed in the gaseous phase. The order of basicity of amines in the gaseous phase follows the expected order. Tertiary amine is greater than secondary amine, is greater than primary amine, and is greater than ammonia. The trend is not regular in the aqueous state as evident by the pKb values given in table 13.3. In the aqueous phase, the substituted ammonium cations get stabilized not only by electron releasing effect of the alkyl group but also by solvation with water molecules. The greater the size of the ion, lesser will be the solvation and less stabilized is the ion. The order of stability of ions are as follows. Primary is greater than secondary and secondary is greater than tertiary. Decreasing order of extent of hydrogen bonding in water and order of stability of ions by solvation. Greater is the stability of the substituted ammonium cation, stronger should be the corresponding amine as a base. Thus, the order of basicity of aliphatic amine should be primary is greater than secondary and it is greater than tertiary, which is opposite to the inductive effect based order. Secondly, when the alkyl group is small like CH3 group, there is no steric hindrance to H bonding. In case the alkyl group is bigger than CH3 group, there will be steric hindrance to hydrogen bonding. Therefore, the change of nature of the alkyl group, for example, from CH3 to C2H5 results in change of the order of basic strength. Thus, there is a subtle interplay of the inductive effect, solvation effect, and steric hindrance of the alkyl group, which decides the basic strength of alkyl amines in the aqueous state. The order of basic strength in case of methyl substituted amines and ethyl substituted amines in aqueous solution is as follows. C2H5 twice NH is greater than C2H5 thrice N greater than C2H5 NH2 greater than ammonia. CH3 twice NH greater than CH3 NH2 greater than CH3 thrice N greater than ammonia. B. Arylamines versus ammonia. pKb value of aniline is quite high. Why is it so? It is because in aniline or other arylamines, the NH2 group is attached directly to the benzene ring. It results in the unshared electron pair on nitrogen atom to be in conjugation with the benzene ring and thus making it less available for protonation. If you write different resonating structures of aniline, you will find that aniline is a resonance hybrid of the following 5 structures. On the other hand, anilinium ion obtained by accepting a proton can have only 2 resonating structures, in bracket calculate. We know that greater the number of resonating structures, greater is the stability. Thus, you can infer that aniline in bracket 5 resonating structures is more stable than anilinium ion. Hence, the proton acceptability or the basic nature of aniline or other aromatic amines would be less than that of ammonia. In case of substituted aniline, it is observed that electron releasing groups like OCH3, CH3 increase basic strength, whereas electron withdrawing groups like NO2, SO3H, COOH, X decrease it. Second, alkylation. Amines undergo alkylation on reaction with alkyl halides. In bracket refer Unit 10, Class 12. Third, acylation. Aliphatic and aromatic primary and secondary amines react with acid chlorides, anhydrides, and esters by nucleophilic substitution reaction. This reaction is known as acylation. You can consider this reaction as the replacement of hydrogen atom of NH2 or greater than NH group by the acyl group. The products obtained by acylation reaction are known as amides. The reaction is carried out in the presence of a base stronger than the amine, like pyridine, which removes HCl, so form then shift the equilibrium to the right hand side. Amines also react with benzoyl chloride in bracket C6H5COCl. This reaction is known as benzylation. CH3NH2, this is methanamine, plus C6H5COCl, this is benzoyl chloride, will form CH3NHCO C6H5, this is N-methyl benzenamide plus HCl. What do you think is the product of the reaction of amines with carboxylic acids? They form salts with amines at room temperature. Fourth, carbyl amine reaction. Aliphatic and aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide form isocyanides or carbyl amines, which are foul-smelling substances. Secondary and tertiary amines do not show this reaction. This reaction is known as carbyl amine reaction or isocyanide test and is used as a test for primary amines. RNH2 plus CHCl3 plus 3KOH in presence of heat will form RNC plus 3KCl plus 3H2O. Fifth, reaction with nitrous acid. Three classes of amines react differently with nitrous acid, which is prepared in C2 from a mineral acid and sodium nitrite. A. Primary aliphatic amines react with nitrous acid to form aliphatic diazonium salts, which being unstable liberate nitrogen gas quantitatively and alcohols. Quantitative evaluation of nitrogen is used in estimation of amino acids and proteins. RNH2 plus HNO2 in presence of NaNO2 plus HCl will form Rn2 plus Cl minus intermediate. Then again in presence of H2O will form ROH plus N2 plus HCl. B. Aromatic amines react with nitrous acid at low temperatures in bracket 273 to 278 Kelvin to form diazonium salts, a very important class of compounds used for synthesis of a variety of aromatic compounds discussed in section 13.7. C6H5NH2, this is aniline, in presence of NaNO2 plus 2HCl, 273 to 278 Kelvin temperature. C6H5N2 plus Cl minus, this is benzene diazonium chloride plus NaCl plus 2H2O will form. Secondary and tertiary amines react with nitrous acid in a different manner. Sixth, reaction with aryl sulfonyl chloride. Benzene sulfonyl chloride in bracket C6H5SO2Cl, which is also known as Hinsberg reagent, reacts with primary and secondary amines to form sulfonamides. A. The reaction of benzene sulfonyl chloride with primary amine yields N-ethyl benzene sulfonyl amide. The hydrogen attached to nitrogen in sulfonamide is strongly acidic due to the presence of strong electron withdrawing sulfonyl group. Hence it is soluble in alkali. B. In the reaction with secondary amine, N-N-diethyl benzene sulfonamide is formed. Since N-N-diethyl benzene sulfonamide does not contain any hydrogen atom attached to nitrogen atom, it is not acidic and hence insoluble in alkali. C. Tertiary amines do not react with benzene sulfonyl chloride. This property of amines reacting with benzene sulfonyl chloride in a different manner is used for the distinction of primary, secondary and tertiary amines and also for the separation of a mixture of amines. However, these days benzene sulfonyl chloride is replaced by para-toluene sulfonyl chloride. Seventh, electrophilic substitution. You have read earlier that aniline is a resonance hybrid of 5 structures. Where do you find the maximum electron density in these structures? Ortho and para positions to the NH2 group become centers of high electron density. Thus, NH2 group is ortho and para directing and a powerful activating group. A. Bromination. Aniline reacts with bromine water at room temperature to give a white precipitate of 2,4,6 tribromoaniline. Aniline plus 3Br2 in presence of Br2 slash H2 will form 2,4,6 tribromoaniline plus 3HBr. The main problem encountered during electrophilic substitution reactions of aromatic amines is that of their very high reactivity. Substitution tends to occur at ortho and para positions. If we have to prepare monosubstituted aniline derivative, how can the activating effect of NH2 group be controlled? This can be done by protecting the NH2 group by acetylation with acetic anhydride, then carrying out the desired substitution followed by hydrolysis of the substituted amide to the substituted amine. The lone pair of electrons on nitrogen of acetanilide interacts with oxygen atom due to resonance as shown below. Hence, the lone pair of electrons on nitrogen is less available for donation to benzene ring by resonance. Therefore, activating effect of NHCOCH3 group is less than that of amino group. B. Nitration. Direct nitration of aniline yields terry-oxidation products in addition to the nitro derivatives. Moreover, in the strongly acidic medium, aniline is protonated to form the anilinium ion, which is meta-directing. That's why besides the ortho and para derivatives, significant amount of meta-derivative is also formed. However, by protecting the NH2 group by acetylation reaction with acetic anhydride, the nitration reaction can be controlled and the para-nitro derivative can be obtained as the major product. C. Sulfonation. Aniline reacts with concentrated sulfuric acid to form anilinium hydrogen sulfate, which on heating with sulfuric acid at 453 to 473 Kelvin produces para-aminobenzene sulfonic acid, commonly known as sulfonilic acid, as the major product. Aniline does not undergo Friedel-Crafts reaction in briquette alkylation and acetylation due to salt formation with aluminium chloride, the Lewis acid, which is used as a catalyst. Due to this, nitrogen of aniline acquires positive charge and hence act as a strong deactivating group for further reaction. Second, diazonium salts. The diazonium salts have the general formula R N2 plus X minus, where R stands for an aryl group and X minus ion may be Cl minus Br minus H SO4 minus BF4 minus etc. They are named by suffixing diazonium to the name of the parent hydrocarbon from which they are formed, followed by the name of anion such as chloride, hydrogen sulfate, etc. The N2 plus group is called diazonium group. For example, C6H5N2 plus Cl minus is named as benzene diazonium chloride and C6H5N2 plus HSO4 minus is known as benzene diazonium hydrogen sulfate. Primary aliphatic amines form highly unstable alkyl diazonium salts, in bracket refer to section 13.6. Primary aromatic amines form arene diazonium salts which are stable for a short time in solution at low temperatures, in bracket 273 to 278 Kelvin. The stability of arene diazonium ion is explained on the basis of resonance. 13.7 Method of preparation of diazonium salts. Benzene diazonium chloride is prepared by the reaction of aniline with nitrous acid at 273 to 278 Kelvin. Nitrous acid is produced in the reaction mixture by the reaction of sodium nitrite with hydrochloric acid. The conversion of primary aromatic amines into diazonium salt is known as diazotization. Due to its instability, the diazonium salt is not generally stored and is used immediately after its preparation. C6H5NH2 plus NaNO2 plus 2HCl in presence of 273 to 278 Kelvin temperature, C6H5N2 plus Cl minus plus NaCl plus 2H2 will form. 13.8 Physical properties. Benzene diazonium chloride is a colorless crystalline solid. It is readily soluble in water and is stable in cold but reacts with water when warm. It decomposes easily in the dry state. Benzene diazonium fluoroborate is water insoluble and stable at room temperature. 13.9 Chemical reactions. The reactions of diazonium salts can be broadly divided into two categories, namely A. Reactions involving displacement of nitrogen and B. Reactions involving retention of diazo group. A reaction involving displacement of nitrogen. Diazonium group, being a very good leaving group, is substituted by another group such as Cl minus, Br minus, I minus, Cl minus, and OH minus, which displace nitrogen from the aromatic ring. The nitrogen formed escapes from the reaction mixture as a gas. First, replacement by halide or cyanide ion. The Cl minus, Br minus, and Cl minus nucleophiles can easily be introduced in the benzene ring in the presence of copper 1 ion. This reaction is called Sandmeyer reaction. ArN2 plus X minus in presence of Cu2Cl2 slash HCl, ArCl plus N2 will form. In presence of Cu2Br2 slash HBr, ArBr plus N2 will form. In presence of CuCN slash KCN, ArCN plus N2 will form. Alternatively, chlorine or bromine can also be introduced in the benzene ring by treating the diazonium salt solution with corresponding halogen acid in the presence of copper powder. This is referred as Gattermann reaction. ArN2 plus X minus in presence of Cu slash HCl, ArCl plus N2 plus CuX will form, and in presence of Cu slash HBr, ArBr plus N2 plus CuX will form. The yield in Sandmeyer reaction is found to be better than Gattermann reaction. Second, replacement by iodide ion. Iodine is not easily introduced into the benzene ring directly, but when the diazonium salt solution is treated with potassium iodide, iodobenzene is formed. ArN2 plus Cl minus plus Ki will form ArI plus KCl plus N2. Third, replacement by fluoride ion. When arene diazonium chloride is treated with fluoroboric acid, arene diazonium fluoroborate is precipitated, which on heating decomposes to yield aryl fluoride. ArN2 plus Cl minus plus HbF4 will give you ArN2 plus BF4 minus in presence of heat. ArF plus BF3 plus N2 will form. Fourth, replacement by H. Certain mild reducing agents like hypophosphorus acid, in bracket, phosphonic acid or ethanol reduce diazonium salts to arenes and themselves get oxidized to phosphorus acid and ethanol respectively. Fifth, replacement by hydroxyl group. If the temperature of the diazonium salt solution is allowed to rise up to 283 Kelvin, the salt gets hydrolyzed to phenol. Sixth, replacement by NO2 group. When diazonium fluoroborate is heated with aqueous sodium nitrite solution in the presence of copper, the diazonium group is replaced by NO2 group. B. Reaction involving retention of diazo group. Coupling reactions. The azo products obtained have an extended conjugate system having both the aromatic rings joined through the nitrogen double bond nitrogen bond. These compounds are often colored and are used as dyes. Benzene diazonium chloride reacts with phenol, in which the phenol molecule at its para position is coupled with the diazonium salt to form para-hydroxy azobenzene. This type of reaction is known as coupling reaction. Similarly, the reaction of diazonium salt with aniline yields para-aminobenzene. This is an example of electrophilic substitution reaction. 13.10, Importance of diazonium salts in synthesis of aromatic compounds. From the above reactions, it is clear that the diazonium salts are very good intermediates for the introduction of FCl, Br, I, Cn, OH, NO2 groups into the aromatic ring. Aryl fluorides and iodides cannot be prepared by direct halogenation. The cyano group cannot be introduced by nucleophilic substitution of chlorine in chlorobenzene, but cyanobenzene can be easily obtained from diazonium salt. Thus, the replacement of diazo group by other groups is helpful in preparing those substituted aromatic compounds which cannot be prepared by direct substitution in benzene or substituted benzene. Summary: amines can be considered as derivatives of ammonia obtained by replacement of hydrogen atoms with alkyl or aryl groups. Replacement of one hydrogen atom of ammonia gives rise to structure of the type RNH2 known as primary amine. Secondary amines are characterized by the structure R2NH or RNHR- and tertiary amines by R3N, RN, R-, R double dash or R2N, R-. Secondary and tertiary amines are known as simple amines if the alkyl or aryl groups are the same, and mixed amines if the groups are different. Like ammonia, all the three types of amines have one unshared electron pair on nitrogen atom, due to which they behave as Lewis bases. Amines are usually formed from nitro compounds, halides, amides, imides, etc. They exhibit hydrogen bonding, which influence the physical properties. In alkyl amines, a combination of electron releasing, steric, and hydrogen bonding factors influence the stability of the substituted ammonium cations in protic polar solvents and thus affect the basic nature of amines. Alkyl amines are found to be stronger bases than ammonia. In aromatic amines, electron releasing and withdrawing groups respectively increase and decrease their basic character. Aniline is a weaker base than ammonia. Reaction of amines are governed by availability of the unshared pair of electrons on nitrogen. Influence of the number of hydrogen atoms at nitrogen atom on the type of reactions and nature of products is responsible for identification and distinction between primary, secondary and tertiary amines. Para-toluene sulfonyl chloride is used for the identification of primary, secondary and tertiary amines. Presence of amino group in aromatic ring enhances reactivity of the aromatic amines. Reactivity of aromatic amines can be controlled by acylation process, that is by treating with acetyl chloride and acetic anhydride. Tertiary amines like trimethylamine are used as insect attractants. Aryl diazonium salts usually obtained from aryl amines undergo replacement of the diazonium group with a variety of nucleophiles to provide an advantageous method for producing aryl halides, cyanides, phenols, and arenes by reductive removal of the diazo group. Coupling reaction of aryl diazonium salts with phenols or aryl amines give rise to the formation of azodies.